Sometimes we run into a sequence of numbers that shows a certain kind of pattern which we refer to as a geometric sequence. So, for example, if you have the numbers 2, 4, 8, 16, those are all powers of 2. And if we see a sequence of consecutive powers like that, we call it a geometric sequence. 1, 2, 4, 8, 16, 32, 64. Those are all powers of 2, right? 64 is 2 to the 6th. 32 is 2 to the 5th. And if you go back to the beginning here, 1 is actually 2 to the 0. So we can see that all of the numbers in this list are consecutive powers of 2. 2 to the 0, 2 to the 1, 2 to the 2, etc. So that's a geometric sequence. This is another geometric sequence. This time we have consecutive powers of 3. This is 3 to the 1. 9 is 3 to the 2. 27 is 3 to the 3. And this sequence shows that we're going all the way up to 3 to the 10th. These 3 dots here, that ellipsis symbol, tells us that the pattern between here continues. So even though we're not writing out 81 and all the other powers of 3 in between, we're supposed to imagine that they've been written there. Okay, so that's another geometric sequence, consecutive powers of 3. Here are consecutive powers of 1/2, right? Because this is 1/2 raised to the 1. 1/4 is the same as 1/2 raised to the 2. 1/8 would be 1/2 raised to the 3. And this expression at the end is 1/2 raised to the 8. So those are consecutive powers of 1/2. And so that's another geometric sequence. This is an example of something that's not a geometric sequence. Notice that instead of these being powers of some number, they're going up by the same amount each time. We add 2 to get from the first number to the second number. We add 2 again to get from the second number to the third number. 2 again to get from the third number to the fourth number. So we're adding 2 every time. And that's not a geometric sequence. That's actually another kind of sequence of numbers that has its own name. It's called an arithmetic sequence. But we're not going to have need for arithmetic sequences in this section. So we're only going to be interested in geometric sequences corresponding to consecutive powers of some number. And in particular, we're going to be interested in finding the sum of such a sequence. What do we get if we add together a bunch of consecutive powers of some number? So for example, let's say I add 2 to the 0 plus 2 to the 1 plus 2 to the 2, etc., all the way up to 2 to the 10th. And it's not written here, but there's supposed to be an ellipsis. So what would that total? Well, you could type all those numbers into a calculator, but if this exponent was a lot bigger, like 2 to the 100, that would be a lot of typing. So we're actually going to see if we can come up with a better way to do this. What we want to do is, in general, find a formula for a geometric sequence that starts with an exponent of 0. So this r here is r to the 1, and the 1 we see at the beginning is r to the 0. It doesn't matter what our base is for r. For any positive or negative number r, the first few powers of r, starting with 0, ending with the nth power, would look like this. And so we want to find a formula for adding up those powers of r. So let's call that sum by a letter s so that we can refer to the sum with a single symbol. And let's take this equation that we've written down here and multiply both sides by 1 minus r. Now, it's not going to be clear why we're doing that until you see how it gets us a formula. But it turns out this is a good first step to come up with the formula. I multiply both sides of this equation by 1 minus r, so that gives me a 1 minus r on the left and a 1 minus r on the right. And then the next thing I'm going to do is distribute. So I'm leaving the left side alone, but I'm distributing on the right side. So distributing means I take the 1 here and multiply it by every term that I see in the second set of parentheses. So 1 times r, or 1 times 1, 1 times r squared, etc. That gives me this. And then I also have to distribute the minus r here to everything in the second set of parentheses. So minus r times 1, minus r times r, minus r times r squared. And if I multiply all those out, I get this expression. So minus r times 1 is what gives me this minus r. Minus r times r is what gives me this minus r squared. And minus r times r to the n is what gives me the last term, minus r to the n plus 1. Multiplying r times r to the n gave me r to the n plus 1. Now take a look at what we've got here, and now you can see why this was a good idea, because we get a bunch of terms that look the same but they have opposite signs, which means they cancel. Plus r and minus r cancel. Plus r squared and minus r squared cancel. All these powers of r here cancel with something over here. This r to the n cancels with the r to the n that's just before the end here. All that's left after you cancel is the 1 and the minus r to the n plus 1. And then finally, we were trying to come up with a formula for s, so we can isolate s here. All we'll do is divide both sides by 1 minus r. And that gives us this formula, which is the formula we're going to use to simplify a sum of terms from a geometric sequence. So this is our general formula, and let's see how we can apply it. I want to find the value of this sum, 1 plus 2 plus 4, all the way up to 2 to the 10. And again, there should be an ellipsis right here. So I'm going to be adding together powers of 2. Right, this is 2 to the 0, 2 to the 1, 2 to the 2, stopping at 2 to the 10. So in this formula, my r is 2, and n, which represents the highest power I run into, is 10. So let's use that. Plug everything in. So where we have an r on the right side, we replace it with 2. Where we have an n, we replace it with 10, and 10 plus 1 is what gives us this 11. And then there's another r in the denominator that also we replace with a 2. Okay, so this you can evaluate on a calculator, and it comes out to a nice whole number, 2047. Let's look at one more. Let's find the value of another sum of geometric sequence terms. So this time we're looking at powers of 1/3, ending with 1/3 raised to the 7th. So our r in this formula is 1/3, and the highest power we run into is 7. So our formula, we plug in 1/3 for r, we plug in a 7 for n, giving us an exponent here of 8. And this expression, you could evaluate it exactly as a fraction, but for the purposes of this example, we'll just plug it into our calculator and get a decimal approximation, and the value comes out to approximately 1.5.